Florida and OTEC. Energy, the environment, the economy. By way of introduction, my name is Jim Baird. I'm a Canadian inventor. 25 years ago, I patented the subductive waste disposal method, which has been described as the state-of-the-art and most viable solution to the problem of nuclear waste. A few weeks ago, it was described as the perfect solution to the problem, but it has never been implemented. Florida's spent fuel problem and that of the rest of the world has therefore gone unaddressed, and nuclear's potential to address global warming has waned partly as a result. I became interested in ocean thermal energy conversion, or OTEC, in the early 80s, when consideration was starting to be given to producing the mineral wealth dissolved in and laying under the oceans. In the past 5 years, it has been revived, and with the realization that it can have significant environmental benefits, even as it produces as much energy as we currently derive from fossil fuels. Global warming is arguably the most compelling problem currently facing mankind. Average Earth temperatures have been rising unambiguously since 1910. Most of the heat is accumulating in the oceans, mostly in their upper layers. The movement of some of this surface heat into deeper water in the western equatorial region of the Pacific, believed to be driven by stronger than average trade winds, has led to the atmospheric warming hiatus of the past 13 years. Climate skeptics have seized on the leveling of the temperature trend as evidence global warming has ground to a halt. In reality, the hiatus is a lesson from nature on how to deal with the warming problem. As can be seen from this graph, the trend line in red from 2001 to 2012 actually declines. If you were to plot the trend line from 1975, however, or from any point back to 1910, the trend would be upward. As is evident from this chart from the 2012 paper World Ocean Heat Content and Thermospheric Sea Level Change 0 to 2,000 meters, 1955 to 2010 by Levitas et al., the heat that has gone missing from the atmosphere the past 13 years has gone into deeper water. Levitas points out, to a depth of 2,000 meters, the oceans have warmed by an average of 0.09 degrees Celsius over the 55-year span of the study. Average surface temperatures over land and sea have increased almost 4 times as rapidly, or roughly 0.85 degrees Celsius from 1880 to 2012, according to the Intergovernmental Panel on Climate Change. The average depth of the ocean is 4,267 meters. Therefore, they have an even greater capacity to absorb heat with relatively limited impact. The oceans play a major environmental role. Their top few meters can store as much heat as the entire atmosphere. Because of their huge mass, they can accumulate a great deal of heat without a significant increase in their temperature. In a recent interview, James Lovelock was asked, "Is climate change going to be less extreme than you previously thought?" His response, "We were taken in by the perfect correlation between temperature and CO2 in the ice core analysis, from the ice sheets of Greenland and Antarctica studied since the 1980s. You could draw a straight line relating temperature and CO2, and it was such a temptation for everyone to say, well, with CO2 rising, we can say in such and such a year it will be this hot. It was a mistake we all made. We shouldn't have forgotten that the system has a lot of inertia, and we're not going to shift it very quickly. The thing we've all forgotten is the heat storage of the ocean. It's 1,000 times greater than the atmosphere and the surface. You can't change that very rapidly." Lovelock's point goes to the ocean's thermal inertia. In retrospect, it is hard to see how men of science could have missed this. Indicative of the kind of benefit we are deriving from the ocean heat absorption, Levitas pointed out if the 0.09 degrees Celsius the oceans have absorbed was instantly transferred to the lower 10 kilometers of the atmosphere, it would warm on average 36 degrees Celsius. This would spell our demise and that of most other species, but fortunately will not happen that way. At least not for centuries, it is believed it will take at least 1,000 years for the oceans and the atmosphere to come back into equilibrium once we stop adding greenhouse gases to the atmosphere. Just as the oceans are slow to heat up, it will take a long time for them to cool down by giving back their heat to the atmosphere. This means the atmosphere will continue to warm for centuries, even after we quit adding heat to the ocean. Ocean thermal energy conversion, or OTEC, uses the temperature differences between cooler deep and warmer shallow ocean waters to run a heat engine to produce useful work, usually in the form of electricity. It is constant baseload power that emits no greenhouse gases. The most recent IPCC study found that taking into account the life cycle of various means of production of electricity, ocean energy was the second lowest generator of CO2 per kilowatt hour. Hydro was the best, but it has limited capacity. Life cycle emissions include all of the carbon dioxide released during the construction, operation, transmission, and decommissioning of various sources of energy. This is the chart of the emissions by technology. Of interest, ocean energy produces half the emissions of nuclear power that is often touted as the best environmental option, and it is 125 times better than coal. This is a diagram of a conventional OTEC design. To overcome the low thermodynamic efficiency of the system, conventional designs move massive amounts of water first to boil a working fluid to produce power, and then bring about half again as much cold water near the surface to condense the vapor so that the cycle can be repeated. To produce 100 megawatts of power with such a system, a cold water pipe of about 10 meters diameter and a length of 1,000 meters is required. Pipes of this magnitude are costly, as are the infrastructure required to support them. The movement of large volumes of water in these pipes can be detrimental to marine life, and the drop in pressure as the water rises to the surface can cause the CO2 dissolved in the water to be released into the atmosphere. Cost and these environmental drawbacks have been the principal impediments to the advancement of OTEC, plus the fact that its environmental benefits have not been sufficiently highlighted. The fastest and most efficient way to move large volumes of heat is with a heat pipe. These are the same kind of devices PCs, tablets, and smartphones use to dissipate unwanted and damaging heat. They are sometimes described as thermal superconductors because of the high heat transfer coefficients for boiling and condensing working fluids. A heat pipe can move heat away from areas where it might do damage at speeds approaching the speed of sound. By inserting a turbine into the vapor flow of such a pipe, electricity can produce the same as it is with the conventional design. This is a basic diagram of a heat pipe. The improvements of this design over the conventional design are: the piping can be one order of magnitude smaller. There is a commensurate decline in the cost of the system. The parasitic losses of the system are reduced because of the ability to move a much greater volume of heat in a working fluid rather than in water. Only a small volume of condensed vapor has to be pumped back to the surface. Marine life is not impacted by the movement of vapor or the returning working fluid, which cycle in a closed system. CO2 remains dissolved in seawater. Parasitic losses are things that take away from an engine's ability to produce energy or that rob it of power. In an OTEC system, these include friction in the turbine and generator, but mainly it is the power used to run the pumps that move the water and the working fluid. The heat pipe is the fastest way to move heat from the surface into the deep. On the surface, ocean heat drives tropical storms. A unit of heat at a depth of 1,000 meters produces less sea level rise than the same unit on the surface because at depth the coefficient of expansion of seawater is half that of the tropical surface. On the lower scale, a d-bar or decibar is approximately a meter of depth in water. The left-hand scale shows the thermal coefficient of water. At 1,000 meters, where heat would be relocated with OTEC of the heat pipe design, the coefficient is less than half that at the surface. What this means is if you warm the ocean at the surface by 1 degree, it will expand twice as much as if you warm the water at 1,000 meters by 1 degree. It is clear, therefore, there is a significant sea level benefit to be derived from cooling the ocean surface by moving heat to deeper water. OTEC, using a heat pipe design, operates virtually the same as a car's air conditioner. A refrigerant is boiled in an evaporator. This process absorbs a great deal of heat because the latent heat of evaporation of a fluid is much higher than its specific heat. The vapor exits the evaporator and at that point can drive a turbine attached to a generator. It then moves to a condenser where the heat is dissipated into a heat sink, pumped back to the evaporator to restart the cycle. A New York father was recently charged with criminal negligent homicide arising from the death of his 7-month-old son, who he accidentally left unattended in his car for a half hour. If he had left his son in the car with an air conditioner running, there would have been no problem. OTEC in effect would operate the same way, but by taking heat away from the surface and the atmosphere, where it can do us great harm, and moving it to the deep where it would be benign. Key amongst the 8 climate risks identified by the IPCC in its latest report, Climate Change 2014 Impacts, Adaptation and Vulnerability, is storm surge, coastal flooding, and sea level rise for coastal communities. Florida is the coastal state at greatest risk to these threats. Miami is the coastal city at greatest financial risk in all of the world, according to a 2008 OECD report. Research published by the Niels Bohr Institute suggests there could be a 10-fold increase in hurricane frequency if the climate becomes 2 degrees Celsius warmer, which business as usual makes virtually a certainty, with increases of from 3.7 to 4.8 degrees Celsius a strong possibility. At the higher range, life on Earth will be fundamentally changed. The combination of sea level rise and increased storm frequency will be devastating for Florida. The top 10 cities in the OECD study in terms of ranking of assets exposed are Miami, Greater New York, New Orleans, Osaka, Kobe, Tokyo, Amsterdam, Rotterdam, Nagoya, Tampa Bay, St. Petersburg, and Virginia Beach. Half are in the United States. For Miami alone, the risk is set at $3.5 trillion, but this is for only a half a meter of sea level rise. The IPCC estimate is 1 meter by the end of this century, and some put it much higher. In 2005, the insurance company Allianz put the total risk to assets in the world's largest coastal cities at $28 trillion, and this was based again on a half meter of sea level rise. OTEC can effectively air condition the planet by converting heat to work and moving exponentially more of it to the relative safety of deeper water. Effectively, the use of a heat pipe replicates the conditions that have precipitated the global warming hiatus, only more so. The trade winds moved surface heat about 100 to 300 meters deeper. OTEC, using a heat pipe, would triple this relocation of the heat, making its return that much more difficult. Flooding and sea level rise are reduced by the relocation of heat to a region of reduced coefficient of thermal expansion. Moving heat away from the surface also saps the energy of tropical storms that bring with them the dual threats of wind and low-pressure driven storm surge. Implemented at a massive scale, OTEC would moderate atmospheric temperatures by moving heat into the ocean deep, and in so doing would benefit marine and coastal ecosystems by reducing thermal stratification that cuts phytoplankton off from the nutrients they need to survive. These phytoplankton are the base of the ocean food chain and the lungs of the planet, as they provide half of the oxygen we breathe by consuming CO2 in the ocean. In the short term, there may be some potential for localized adaptation to the 1/2 to 2 meters of sea level rise that is anticipated by the end of this century. In the long run, however, there is no adaptation to 20 meters of sea level rise and a 10-fold increase in extreme weather. The last time CO2 levels in the atmosphere were as high as they are today, sea levels were 20 meters higher. There are only 3 options for Florida in the face of the climate impacts the state faces: trying to reduce the rate of rise, or mitigation, coastal defense or retreat, adaptation, or suffering the consequences. Mitigation involves arresting future carbon emissions, which OTEC can do, and results from moving surface ocean heat to deeper water. Adaptation requires becoming more resilient to the expected impacts, but in the long run it is a losing proposition for Florida, as is suffering the consequences. Effective mitigation would be a win-win-win for Florida. Energy is a $6 trillion per year market sector. About 85% of the energy we currently consume is derived from fossil fuels that have created the climate problem. All of this can be replaced by OTEC, which in turn mitigates the sea level rise and storm surge problems that threaten Florida. The design and build-out of the infrastructure that can save Florida and small island nations represents an enormous economic opportunity. The spin-offs from a transition to this new energy paradigm are desalinated water or water reconstituted from hydrogen electrolyzed at sea to bring OTEC power to shore, and recovered dissolved mineral wealth from the oceans. Because the link between ocean heat and global warming was missed 30 years ago and has only casually been made subsequently, the benefits of ocean thermal energy conversion have largely been overlooked at a critical juncture in the evolution of clean energy. Its proponents, therefore, are now struggling to catch up and to find the financing necessary to prototype and prove their designs. Three obvious questions remain to be answered. Will it work? What will it cost? What are the alternatives? The thermodynamic principles of a heat engine are well established. They are the same principles at work in an air conditioner. Nature also operates on these principles. Her response to overheating oceans is a hurricane, which converts heat to mechanical energy and moves more to cooler regions of the planet. The OTEC heat engine turns the hurricane on its head. Mechanical energy drives an electrical generator. Heat is moved to deep water rather than high in the atmosphere to condense a working fluid. A number of PhDs in physics and engineering have patents and applications for variations on the OTEC heat pipe design. Before committing to the expensive large ocean-going prototypes, the theory should be tested at lab scale. A 2010 paper, Economics of Ocean Thermal Energy Conversion, OTEC, an Update, by Luis Vega of the University of Hawaii, puts the cost of OTEC-produced electricity at less than 18 cents a kilowatt hour, or about mid-range in the following study based on IEA data. It should be noted the highest cost on this chart is Denmark, that has been instrumental in the development of contemporary wind energy and is highly dependent on that source. Vega's cost is based on a design using a cold water pipe. The deep water condenser design has the potential to shrink the capital cost of an OTEC plant by about 30%, according to Paul Curto, former chief technologist with NASA, due to the reduction in the size of the piping and supporting infrastructure. Vega's costs are for a first of kind. As has been seen with solar and wind, costs come down rapidly with experience and economies of scale. Many environmentalists, including James Lovelock and James Hansen, think that nuclear power is the only practical alternative to coal for producing electricity. Think back, however, to Lovelock's earlier statement. The thing we've all forgotten is the heat storage of the ocean. This ocean heat storage is not without consequence. Sea level rise, increased storm frequency and magnitude, and prolonged impact of climate change are amongst those consequences. Einstein said of nuclear power, it's a hell of a way to boil water. Boiling water is also a hell of a way to generate electricity. It produces twice as much heat as energy, and most of this ends up in the ocean where it adds to the sea level and storm surge problems. OTEC, on the other hand, converts the heat already in the ocean and causing damage to productive use and our environmental benefit. It would be in Florida's energy, environmental, and economic interest to take the lead in the development of this clean energy technology that addresses both the cause as well as the effect of climate change. Thank you for taking the time to consider this presentation.